NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, everybody. Welcome to the Von Karman series from NASA's Jet Propulsion Laboratory. I'm Preston Dyches. Well, this is our monthly series of public talks and discussions, usually brought to you live from our Von Karman Auditorium at JPL, and hence the name of the series. But like so many other shows and live events right now, we're coming to you remotely from our homes spread out across the Los Angeles area. So thank you so much for joining us in trying something a little different. And especially if you're watching us live, because we feel like shared experiences like this are important right now. So, and if you're watching us live on Facebook and YouTube, you can submit questions via the chat, and we'll work in some of those questions during our show. Okay, and to help us with that, I am really grateful to have my colleague from JPL, Shannon Forrey, who is part of the NASA Earth Public Engagement team. Hey, Shannon.
Hi, everybody. Thanks for watching. I'll be sharing your questions with our guests at several points in the show, so keep them coming, and in the YouTube and the Facebook chats. And if you're not seeing the chat window, just refresh your browser, and it should appear.
All right. Well, thanks, Shannon. I just want to note that since this is an experiment and we are recording live, if we run into any technical challenges, we will roll with them, and we hope you'll hang in there with us as well. So that brings me to a program note. We had planned to bring you two speakers tonight, with one of them being a scientist on NASA's Delta X mission, but unfortunately, due to a technical issue, we weren't able to have them join us. But we will still have a great discussion with our other speaker, and we'll actually talk a little bit about the Delta X mission anyway, and hopefully we can share more about that really exciting mission in a future show. So perhaps because of the extraordinary situation that we're all in right now around the world, it feels like a particularly relevant time to remember our shared responsibility for planet Earth. And remember that in the biggest sense, we really are all in this together. And so to that end, we're coming up on Earth Day. And that's on April 22nd, and it's not just any Earth Day. This is the 50th anniversary of Earth Day this year. And Shannon, you've been deeply involved in NASA's planning for what we're calling Earth Day at Home. So can you tell us what NASA's got planned?
Yeah, well, like we do every year, NASA plans to observe Earth Day and share a variety of resources about the beauty and wonder of our amazing home planet and what we're doing at NASA to study and better understand how it's changing. And so you can visit nasa.gov/Earth Day to find all of our Earth Day resources in one place. And you can also follow us on @NASA-Earth on social media channels and follow along with all of our Earth Day activities on #EarthDayAtHome.
All right. Fantastic. So to connect to Earth Day, as Shannon talked about, we're talking this month about observing our home planet. And we're fortunate to have with us a NASA Earth scientist who is helping to lead an important mission to learn more about planet Earth. And we'll talk with him about his mission and also the bigger picture of the whys and the hows of studying Earth from above and below. And so I want to welcome our guest, Paul Rosen.
Hello there, everyone.
Hey, Paul. Paul serves as the project scientist for NASA's NISAR mission. So great to have you with us, Paul.
Thank you.
So I want to start off really big picture. Why is it that we need to study our home planet? It seems like it's pretty well explored, at least the land surface. What else do we need to understand about Earth beyond just keeping up with the weather?
Well, it is true that people have been living on the Earth for a very long time, and we've measured quite a few things on the Earth over the centuries. So I like to think of it in terms of medical research. We're very familiar with our bodies and our minds, yet we continue to study our bodies and our minds and invest very heavily in doing that. When we're well, we don't usually think very much about what's going on with our bodies. But when we're sick and when we recover, we often want to understand why that's the case. And we want to figure out ways to prevent ourselves from getting sick in the future. At this particular time, as you mentioned, with the coronavirus epidemic, biological forces on our bodies are at the forefront of our mind right now. But there's other forces as well. There's stresses of everyday life. There's environmental stresses. There's geophysical stresses, such as earthquakes and volcanoes, sea level rise, and many, many factors that go into understanding us as human beings. And the same is true for the Earth itself. There's inputs and outputs. There's energy sources and energy sinks. And it's a very complex system, just as our bodies and minds are very complex systems. So it's important for us to study the ocean, study the atmosphere, study the solid Earth, the crust, and how it changes with time. Study the ice sheets and how they change and how they interact with the oceans and the atmosphere, in order to answer some very important questions to all of us. What's going to happen to my house when the next earthquake occurs here in California? If there's a drought in a particular country or region, what does that mean in terms of this year versus 10 years? Is this a permanent condition? Is our climate changing in the sense that we would expect this forever? When the Amazon burns, as we observed last summer, how is that actually changing things? Is it a long-term effect or a small-term effect? This is all very complex system science at the Earth level, and there's a lot at stake in these observations, so it's extremely important to study.
Well, everyone who's watching may not be aware that NASA actually studies Earth both from high up in space in orbit and also down from closer to the ground from using airplanes and surface instruments and boats and things. So why, that kind of gets to the theme of our show. So why is it important to study Earth from different vantage points, from space and from closer to the surface?
Well, there's many different reasons for it. I'll try to summarize quickly. Some things you simply can't measure very easily from space or as well as you could do from, say, the ground. An example might be if you want to study the age of a tree by measuring tree rings, it's much more simple to get a tree coring device and cut a hole into the tree and look at the rings. Or if you're looking at the ages of the ice sheets over the last 200,000 years, it's easier to drill a hole and core the ice and look at the layers of the ice than it is to measure that from space. There are space techniques to do those kinds of things, but certainly an in situ, in place measurement such as that is quite effective and quite cost effective. However, if you want to do that everywhere, it's very difficult to send an army of people to every tree in the entire forest of the Amazon or the Congo or the northeastern United States and measure such a detailed set of measurements. So we often then go up to the air or we go up to space. In the air, we will look for some other technique, some other instrument that could be a proxy for something like measuring the tree rings, the age of a tree. And some of the measurements we'll talk about later today are related to that. In air, we would perhaps focus on things that are best observed in a way that a satellite from space could not do. So for example, we're going to talk about a mission later, the Delta X mission, briefly. I understand the speakers are not here tonight. But in that particular case, it's an airborne mission to look at delta regions of rivers, and they are extremely dynamic. And they can change with the tides. They can change on a daily basis as the weather conditions are changing. So you need to sample those in space and time quite effectively, quite fast, effectively. So that's very difficult to do from space because you are fixed in a particular set of orbits. And so that particular observation is best suited to an airborne system. From space, of course, we get the vantage point of looking at the entire planet, assuming we pick an orbit that's associated with that. And there's a particular orbit that we use, and we can have a swath that will cover the entire Earth and then give us that global perspective. Right. So that's the reason why we sometimes look on the Earth, sometimes we look in air, and sometimes we look in space.
Yeah, it sounds like you really do need a multifaceted perspective to kind of see the big picture, is what you're saying.
That's exactly right.
And I think, Shannon, you've got our first question from the live audience. Why don't you go ahead?
I do, yeah. So Chris on YouTube asks, do we ever consider the Earth's carrying capacity, world population, and its impact on climate change?
Yes, we certainly do worry about that. Food security is one very important factor in sustainability of the human condition, and food security is related to agricultural production, and agricultural production is related to how we treat our environment and climate and that kind of thing. So yes.
It's basically all connected.
Yeah.
So Paul, Earth science is one of those areas where NASA collaborates a lot with other agencies like NOAA and the U.S. Geologic Survey, as well as other countries, but we'll talk a little more about that in a minute. But if other government agencies are studying Earth and observing it, why does NASA do that too? What is our role in the story?
Well, the simple answer is that NASA has a charter to study Earth science from space using new technologies that are developed through the space program, driven by those science requirements. That's the simple answer. Now, of course, it's a little bit more complex than that. NOAA has satellites. They measure weather. It's an operational agency to measure the weather. It's not really science driven. Some science can be done with their satellites, but generally speaking, they take proven techniques, proven satellites, fly them, and give us the weather on the Weather Channel every night. That's one of their main roles. NSF, the National Science Foundation, they have a charter to do Earth science as well as many other sciences, but they generally are not a spacefaring agency. They have programs that are related to those, but it's not their charter to actually do that with new technologies. And USGS similarly has a mandate to monitor everything about the country, basically, not necessarily the globe, although they do have global initiatives as well, about water quality and management of forests and things like that. They tend to be less focused on this charter of whole system science using new technology from space. So NASA does have a unique role in this capacity.
All right, well, let's, Shannon, you got another question. Why don't you go ahead?
I do, and I might be getting a little ahead of myself here, but Manish on YouTube asks, how will we benefit from NISAR's mission research?
Why don't we come back to that one in just a minute? We'll let Paul
I think,
build up to that.
We're going to have a lot to say about that as we go forward. Yeah.
So how about this? Let's answer that question right now.
Exactly.
All right, let's get started then talking about these two examples, these kind of specific examples from the many, and I mean many, different Earth science missions and programs that NASA supports. These are two upcoming missions, NISAR and Delta X, meaning they're still in development, getting ready to deploy. And they're very different types of missions. And so together they give a sense of the wide range of methods and perspectives that NASA uses to help understand how our planet works and how it changes. So let's answer that question. Let's talk about NISAR, Paul, starting with what is it?
Well, NISAR is a fantastic mission that I have the honor and privilege to be the project scientist for. NISAR is an acronym. So it's a set of words that are put together into an acronym. N stands for NASA. So that's another acronym. The I stands for ISRO, which is another acronym, stands for the Indian Space Research Organization. And the S stands for synthetic. The A stands for aperture, and the R stands for radar. So NASA ISRO Synthetic Aperture Radar mission. Very complicated. We tried to come up with a better name, but it was very difficult, and we just stuck with that. So it describes that we are in a partnership with the Indian Space Research Organization. NASA and ISRO are equal partners building this satellite together. And I like to think of the satellite as effectively a radar that makes 3D time-lapse movies of the Earth. And we'll talk about the aspects of that in a bit, but first I thought I'd kick it off by showing an animation, which is kind of like a 3D animation of the spacecraft itself. That would be graphic number 1. That could be brought up. So this is showing in 2 years from now, when we launch in 2022, the spacecraft is stuffed into an Indian space vehicle, and then it has to be deployed. So here you can see the deployment of a very complex boom with 4 joints. You can see the boom is now being extended to its 9-meter length, and then it rotates up and gets into its final position to deploy a 12-meter diameter, that's 36 feet roughly, reflector, gold mesh reflector. So this is a huge system that we are launching into space. 12-meter reflector, 9-meter boom, and a 5-meter spacecraft packed with electronics, 2 radars, one from NASA, one from ISRO, and a lot of telecommunications equipment to get a huge volume of data from space to the ground. So that's what the system is, and these 3D IMAX movies are to measure deformation. And the technique that we use for that is by taking an image, comparing it to the image at another time step, and another time step, and another time step, and looking at these images as a meter stick to measure the motion of the Earth to millimeter precision, and the changes in the reflectivity of the Earth to very, very high precision as well over time. So we can see changes of all the land and all the ice-covered surfaces over the life of the mission.
Wow. So to millimeter precision from space.
Yes,
That's
from
pretty,
space.
pretty
From
impressive.
1 million meters of space, you can measure it to 1,000th of a meter precision. It's really phenomenal.
Very cool. Well, tell us more about how you do it. I mean, you use you use radar, right?
Yes. Okay. Well, let's see. First of all, let's look at graphic number 3, which shows you an animation now of how the system operates. So we're flying along at 7,500 kilometers per second, and we're sending pulses to the ground roughly 1,000 times per second. So each one of these little potato chips you see flying to the ground is traveling at the speed of light, measuring that then reflects off the surface, and some of that energy goes back to the radar and is received. Now, as you collect that data, you can see that as you collect more and more pulses, you can build up resolution of the image. That's in the top right portion of your image. You get a radar image like that that is high resolution after you collect enough of these pulses to do so. So that's the synthetic aperture part. It's like having a very large lens in space that's 10 kilometers long. It's not that long, but it's synthetically that long by processing the data in a particular way to get this high resolution imagery. Then once we have that image, we fly over the same spot again, make another image that looks just like it, and you can think of the radar wave that we transmit kind of like a meter stick. And we're measuring the changes in the length of that meter stick as the Earth moves below the satellite.
Very cool. So Shannon,
Yeah.
did you say you have another question for us?
Yeah, actually, I'm going to throw 2 at you right now, Paul. So we have William on YouTube asks, how do we prevent congestion or collisions around Earth with so many missions and satellites observing Earth?
Well, that's an excellent question. And I wish I had a really good answer to that. But at some level, there is coordination internationally to when you launch a satellite to make sure that you're not launching it in a place that another satellite exists. So there is that degree of coordination. There are sometimes places where you don't want to launch a satellite because you know there's a lot of debris there from perhaps a collision, a previous collision where there's debris all over the place. You want to avoid that. But at some level, sometimes these things do hit other objects in space, and you do have to be a little bit careful. But from spacecraft to spacecraft, it's pretty well coordinated. All the spacecraft are tracked. Everybody knows where they are, and they tend not to collide. Space is also extremely large, so it's relatively easy to avoid hitting another satellite.
So in addition to solving the pressing problems of space travel, you do actually have to worry about that, to some extent with NISAR, right? You will be concerned about the health and safety of your spacecraft, but I guess you're saying we do a pretty good job of watching out for the dangerous stuff.
We do, and in fact, there are people who monitor the environment that we're flying in on a daily basis, and they will make a recommendation to the project to tweak the orbit a little bit to move one side or the other in order to avoid a piece of space debris. It's generally not another satellite because we know where they all are, but for space debris, sometimes we have to worry.
Okay, hit us again, Shannon.
We do track that.
And then a little bit to an earlier point, as Lauren on YouTube was wondering, how do these partnerships and collaborations start with other countries?
Well, that's also fascinating. It's a very long story for NISAR. We actually started this back in 2008 to try to get a partnership going. It's partly a result of persistence and knowing your colleagues around the world and trying to line up your program with their program. For this particular mission, we talked to many different countries, trying to find a way to partner with them. NASA told us quite explicitly, you must partner because this is a very large mission doing very large science and it's quite expensive. So finding a partner was essential to making it happen. And it just turned out, after talking to maybe 4 or 5, 6 different possible partners, I actually went to India all by myself for the first time back in 2011 and told them about the mission. And it turned out that they were thinking about almost the same concept for observation with the same kind of radar. And the timing of the program was roughly equivalent to our timing. So we were very lucky in this case, but in general, it requires persistence and coordination at the international level to make these happen.
So we'll come back to the science. I know we want to talk about the science of NISAR, but let's stick with that the partnership just for a moment and just ask what India's role in the mission is going to be. They're launching the spacecraft for one thing.
Yes. They're an equal partner in every sense of the word. They have a science team that is joint with our science team, and their objectives tend to focus in India and the surrounding countries, but they also have objectives globally for looking at ice sheets and forests and other things like that. They are also building we call it the spacecraft bus, that part of the satellite that controls the orbit and that has the power system that provides the power to all of the radars. And they also are providing one of the 2 radars. So let's see, if we could go back to that very first graphic. I don't know if you can, graphic number 1, sort of in the middle. I don't know if you can start in the middle or not, but in any case, in that graphic, you'll see that octagonal structure with the little ladder hanging down. That is where the radar instrument is. The cube behind it is actually the spacecraft bus that's provided by ISRO. So JPL, NASA, is building the octagonal structure with the long wavelength radar that NASA is providing. And also in that structure is mounted the shorter wavelength radar that the Indians are providing. So bus, launch vehicle, science team, S-band radar, short wavelength radar, mission operations. They're providing an enormous, and the data is freely and openly available to the world, both in India and in the US. So it's a very balanced partnership. They're providing a lot.
Well, these international partnerships seem to be increasingly important in space exploration, and they're a wonderful thing. And it's one of the things that when I first heard about, Shannon told, I think you told me about NISAR, and what's so wonderful about it in this context, in particular for Earth Day, is that's a country on the other side of the planet that we are working hand in hand with for the good of everybody, and that's kind of what we're all about at NASA. We're just trying to learn and to study and provide information, just to help everybody out.
It's a fabulous experience, except for the telecons that occur at 9 o'clock at night with India, because they are literally halfway around the world from Los Angeles. But it's a wonderful, rewarding experience.
Oh, that's great. Well, so let's go back and get into some of the science, because you are the project scientist. You're the lead scientist on the mission. So tell us about what NISAR will study, what it will observe.
All right. So I mentioned that it's like a meter stick. So if you could bring up graphic number 5, this will show you an example of one of these 3D movies that we see. So what you're looking at here is the Los Angeles basin breathing. So here you can see some of the faults in the Los Angeles basin are depicted. The color here, going from red to blue and back again, is basically the surface level elevation of the Earth. And you can see it's going up and down on a seasonal basis, a yearly basis, as water is extracted from the LA basin. The surface sinks. And as it's re-injected naturally and by people in the wintertime when it rains, its surface rises. So this is, again, about 1 inch, plus or minus 1 inch, or 2.5 centimeters of motion that we're measuring from space. This is from a European satellite that flew many years ago, and you can see there's some holes in the data, and it's not as accurate as we would like. But nonetheless, it shows you quite clearly that we can measure down to millimeter precision the motion of the Earth. So we're studying that kind of motion. This happened to be for studying the aquifers, the subsurface water within the Los Angeles basin. But you can see quite clearly it was related to also the earthquake system, the fault system that's in the Los Angeles basin. So we use this technique to look at the motion of the tectonic plates, to look at volcanoes. Actually, if you could bring up graphic number 6, that shows you something very, very interesting. I don't know if you can see it from very clearly. I can barely see it on my screen here. But you can see sort of a bullseye pattern, which is, again, a depiction of the elevation, the rising of the surface there due to pressure building in the magma below the surface in this particular area. So I think it's up in Oregon someplace. But what's very interesting about this is that the 3 peaks where you would expect to see the bulging, because volcanoes tend to have these beautiful edifices that then explode in an eruption, the 3 peaks are not centered on that bullseye. So what we learn by looking at these kinds of observations is, what is happening below the surface? It's clearly not something that we might expect, that you'd see that bullseye pattern centered on one of those 3 peaks, or maybe all of the 3 peaks as the pressure is building. So we study earthquakes, we study volcanoes, we study landslides using similar techniques, we study aquifer systems. These are pure scientific questions, just understanding the physics, the geophysics of our crust that we live on. They're also very applied problems. What do you do about people living in earthquake-prone areas, in volcanic areas? How do you design society around these physical phenomena? So that's one of the three main disciplines that we have. That's enough, perhaps, for one mission. But we have actually three main disciplines, and then about 20 or 30 other kinds of applications that spin off from those science disciplines. So solid Earth is one of the main disciplines. The other is the cryosphere, studying the ice sheets and sea ice. So if you could bring up graphic number 7, I think many of you know that the ice sheets are intimately related to the sea level. As the ice that's on the ground melts and disappears, that water tends to go into the sea, and that tends to contribute to the rise of sea level. So understanding the dynamics of the ice is extremely important for understanding how the ice sheets are changing, and therefore how the sea level is going to change. So in this graphic, you see on the left of it, it's a colorful image of a glacier. Happens to be in Greenland. It's called Jakobshavn Glacier. And the one on the left is from one time period, I think around 2000. The one on the right is from another time period, about 8 years later, if I recall the numbers. And what you can see is that the location of where that color band ends and turns into gray has changed. It's receded. So the ice has receded. And the other thing you can see is that the color is very different, meaning the velocity. Color represents the velocity of that glacier, so the speed at which the ice is moving. You can see that over that 8-year period, the speed of that glacier, especially in the main part, has increased significantly. So it's shrinking and receding, and this is one glacier out of hundreds in Greenland, and maybe hundreds or thousands in Antarctica, where ice has a mechanism for flowing out into the sea. So making these substantial global measurements as movies allows us to get a complete picture of their dynamics over the life of the mission and put that into geophysical models that allow us then to predict what might happen to these ice sheets over time, factoring in other measurements as well, ocean temperature and accumulation of snow in the winter and things like that. So that's another major thing.
It's just truly amazing. If I can jump in, I think what's baffling or really just astounding is that you can measure that kind of movement of the solid Earth and you're talking about ice now, the cryosphere, with such precision, and what you're really looking for is change over time, like you say, right?
That's correct. Yes. So prior to the modern era, people didn't think much about the ice sheets. They assumed that, it snowed, it accumulated ice, the gravity pushed the ice out into the ocean, and it was a sort of a steady state process. But as we're learning and making more and more observations, we see that it changes on a seasonal basis. It changes over the years. It's driven by tides, and you can see some absolutely fantastic, pure scientific things about the dynamics of the ice on a daily basis even. So it's a complex system that people did not fully appreciate until we had these kinds of measurements. And NISAR, unfortunately, the existing systems, they'll give you a snapshot over a very long period of time. They don't give you this kind of movie-like depiction over the years of the mission to get a really complete picture of it.
So would that be your elevator pitch for NISAR? Is that NISAR makes a movie of planet Earth? That's what we do. We make Earth the movie.
Yeah, and the advantage of radar, as opposed to other systems, is that it's an active source, meaning we have the power up on the spacecraft to transmit a signal to the ground. And it's a long wavelength. The radar wavelength is something like this, and that doesn't interact very much with rain or clouds. So we can actually see right through the clouds. And since we have our own power source, we also don't have to have the sun out. So we can measure 24/7, and every measurement we make is an important measurement. So we get very complete time series over the life of the mission. It's really quite a powerful technique. And we measure fundamentally different things from what most other sensors measure, which are more sort of looking at the chemical structure of plants and land surface. We're looking at the physical structure and the motion of that surface. So it's really quite astounding.
And you said was there one more key pillar of science that you wanted to get to?
Yes. And of course, that one has multiple sub-disciplines. We call it ecosystems, but we're studying biomass, we're studying agricultural crop area and how it's changing over time. We're studying wetlands inundation, and we're studying another one. It'll come to me in a second. But if you could bring up graphic number, let's see, 4, please. This gives you a notion of our observation strategy, highly accelerated. We cover the Earth in 12 days, so 173 orbits over the 12-day period. And this has underneath it simulated biomass. So by biomass, we mean basically the stuff, the carbon that's in the trees. It's directly related to it. We measure the forests because the forests are a very sensitive measure of what's going on within the carbon cycle. And it's actually one of our least well understood measurements for ecosystems and the carbon cycle at the scale that we need to know it. So you can see that we're covering the entire Earth. When this finishes, it's going to stop, and you will see 2 very important areas where we need to know the biomass. One is the Congo in Africa. The other is, of course, the Amazon, where there's an enormous amount of biomass. Now, so there you can see the green areas there. That in South America, that's the Amazon, and the green area in Africa, that's the Congo. These areas have pretty dense biomass, and when you think of them, you might think that they are just sort of there, static. But in fact, there's a lot of activity in those forests, mostly induced by humans, cutting down the trees and creating agricultural areas. So these 2 measurements of biomass change, that was the 4th one, biomass change. We measure the static biomass change, and the agricultural area around the world synoptically, so that we can understand this carbon dynamic and exchange with the atmosphere.
I got to stop you on the word synodic. You got to tell people what the word synodic means. You don't get away with that.
Synoptic means the whole Earth view. We're looking at everything synoptic, all at once. Synodic. Yeah, okay. Synoptic, yeah.
Got it. Okay, well, it's a staggering amount of science and such a wide variety of things that it's going to do. And yes. Shannon has a question about the science you wanted to ask about how you filter the data, right?
Yeah. So we have a question from WFC Striker on YouTube, and he asks, or they ask, how do you filter out things that move on Earth that shouldn't be measured, such as cars, people walking around, or large buildings? How do we filter that out with NISAR?
That's a very technical question, but it's a very good question. So we actually
give us your least technical answer.
The short answer is, because we're looking at these images over time, we get something like 30 images per year from each vantage point. Cars move from one day to the next. They create a little bit of noise in our image. If it's in one place one day and another place another day, then those 2 cars are going to, the car will create noise in the 2 different places where it is on those 2 different days. But because our image pixel size, people know what pixels are, right? Pixel size is fairly large. If you move just one car out of that pixel, most of the pixel stays the same. And so we can actually still get a measurement of the motion of that whole pixel with a little bit of extra noise because the car is in there. So we don't actually actively filter it out. We use our processing techniques to just accept a little more noise. And we take many images in order to reduce that noise. There's many error sources in our measurement, And we use just the volume of data and the time-lapse nature of it and our knowledge of how the Earth is supposed to move to try to filter out that kind of stuff.
I have a quick follow-up to that if you're open. Courtney on Facebook asks, are there any areas that NISAR will not analyze?
That's an excellent question. Yes, in fact, we are unable to reach the very North Pole with this particular orbit. We can measure up to around 77 degrees north latitude with the current plan. Originally, we were going to measure all the way up to around 82 or so degrees north latitude, very close to the pole in the north. But the science team made a decision to look only towards the South Pole. So we image almost all of Antarctica continuously, but we miss the sea ice in the very northern portion. And of course, we're not imaging the oceans. We look at coasts and coastal processes, but not the deep ocean. Cool. And I can say more about why we're not looking at the north if you want, but I think that's probably enough.
We'll come back to it if we have time.
Okay.
So, I mean, it's such an incredible mission. So there's a lot to look forward to. And I'm sure we could talk about NISAR for the whole show, but we wanted to talk a little bit about Delta X. So let's come back down to Earth, so to speak. And I know that's corny. And talk about our other Earth science mission. And Shannon, so as our NASA Earth Outreach Specialist, what do people need to know about Delta X?
Absolutely. If we can pull up image number 11. As a NASA-JPL-led mission, Delta X is one of 5 Earth ventures kicking off in 2020. Over the last 80 years, coastal Louisiana has lost some 2,000 square miles, about 5,000 square kilometers of wetlands, roughly an area the size of the state of Delaware, or on average about 1 football field of land lost per hour. To understand the Mississippi River Delta is one of the largest river deltas in the world and is gaining and losing land. The Delta X mission will use airborne remote sensing and field in situ measurements to look at the water, vegetation, and sediment soil. Delta X is trying to understand some parts of the delta lost and others that gain land. What the role of vegetation and the channel networks in moving and retaining those sediments and building soil. But why deltas? They're home to 500 million people. They're highly rich in productive lands, acting as nurseries for fish, crustaceans, mammals, and birds. And they protect inland areas and infrastructures from winds and flooding during storms, acting as the first line of defense against sea level rise. The loss of deltas will displace millions of people.
All right. Well, thank you for stepping in there, Shannon. Really appreciate you beefing up your knowledge about Delta X. It really is an incredible mission, and it's going to be making some very real scientific impact right here in the U.S. When it gets underway in the near future. So we've got these 2 really fascinating missions. One's up in space, one's down closer to the air with the airplanes and the boats like Shannon showed. Paul, are there connections between these campaigns or ones like them? Are there overlaps between the science that they'll be doing?
Oh, absolutely. As I said much earlier in this broadcast, Delta X is an example of the kind of measurement that we make from airborne systems that we wish we could make from space, but we simply can't. So Delta X, I think, has a radar component as well. And it will fly over the delta and measure these changes with very rapid frequency and at higher resolution than what NISAR can do. So we can use those kinds of observations as essentially validation and calibration of our spaceborne measurements and help with the modeling, because we can do a better time series analysis on these kinds of very fast-moving events from the airborne data and see how that matches with what we see from space. So it's a very synergistic relationship. We actually have an airborne prototype called UAVSAR for the NISAR mission, which is radar with similar characteristics to NISAR, but it flies all over the world taking same kinds of measurements, but with this kind of airborne focus of fast repeat and high resolution.
Very cool. So since these missions and many other, there's a ding.
Yeah, sorry.
Since you're very popular. Since these missions are all about studying change, this is questions and complete setup, but I want to hear what you have to say about it. How do you know you're ever really done? I suspect the answer is that you aren't, because Earth is never going to really stop changing, right?
Yeah, that's right. You probably are never done. There's always more questions to ask. Every time, that's the nature of science, though, right? Every time you think you've solved something, you've modeled something, you ask the next level of question. Think of Newtonian physics, gravity, and then going to special general relativity and trying to understand the nature of all forces. With earth science, it's the same thing. You're going to come up with a model of the ice sheets, and that will help you predict sea level rise. But then the next question is, well, what about the friction on the base of that ice sheet? If we could only measure that a little bit more accurately, we could really drive our model to the next level of prediction and get the error bars down on that climate model to the future, and be that much more precise in how we respond to it. So there's always more questions to answer.
And it seems like one mission begets the next mission, right? You answer the questions that you've got as best you can with the mission you're flying, and then there's a follow-on that kind of picks up the mantle. That's
right. And actually, it turns out NASA conducts through the National Research Council decadal surveys for their Earth science plan for the coming decade. NISAR's a version of NISAR was recommended back in 2007, and 2017 a follow-on to NISAR was already recommended in order to focus on exactly these kinds of measurements over the long term, because not only are they important scientifically to keep that time series going, but it's also the side benefits of studying landslides and other hazards, agriculture, sustainability, all of these things, they just don't end, and they are practical applications of this sort of whole Earth imaging system that will be there forever.
Well, I want to ask you where the information, the research goes once it's collected. So how does it get communicated out from the NISAR team and the NASA folks you work with in a way so as to make it useful and impactful, both for government decision makers and for the public at large? How do you get it out?
Well, that's a multifaceted answer, but I'll try to keep it simple. First of all of our data are free and open to the public, and they are placed in an archive. It happens to be nominally located in Alaska at the Alaska Satellite Facility. But for NISAR, we will be the first mission to actually use cloud-based data distribution systems. So the data may not be in Alaska, but it will be managed out of Alaska. So all those data there will be placed there. That they can be taken by anybody, any company or person for use. For example, companies like Google or Amazon will often take these data and put them into their search engines for geospatial data sets. The science is done by anybody who wants to write a science paper using these data sets. Those are published in journals, typically. And then there is the linkage to our other agencies. And NISAR is trying to do something a little bit unique in terms of our relationship with other agencies. In that, we are trying to create the system not just as a science system, but also something that is let's say a prototype or a test bed for urgent response associated with agencies like FEMA or the USGS. And in doing this, we are creating a low latency pathway for data to go to those agencies and look at things like earthquake damage or volcanic damage or landslide damage quickly after an event, so it can actually be used in a quasi-operational way without making this an operational mission.
Wow.
So that's the way we go about doing it, is to try to build these partnerships and look for pathways for data pipelines into the agencies.
Wow, that's fantastic. So Shannon, I'm sure you've been collecting some questions, so we've got a few minutes left in our hour. Why don't you go ahead and take it away and throw some more of those great questions at Paul from our online audience.
Sure, absolutely. So we have a couple for you, Paul. We have Robert on YouTube who asks, how do you decide what to explore on Earth and the universe? As in, how do you make NISAR a mission?
So that's a good question. This is done through the decadal survey process I mentioned earlier. Science community is brought together as a community, and they meet and make recommendations about what the big topics are, the big things that need to be answered for societal benefit. They write a recommendation, and NASA takes that recommendation and decides which missions they can do, which technologies are ready to be applied to those science questions. And then they go ahead and build the mission.
Well, you mentioned real quick that you had been trying to get this mission going for a long time, right? I mean, the dream of doing a mission like NISAR, has been around for a while, right?
Yes, I wrote my first proposal for a NISAR-like mission in 1994. Let's put it that way. And often it takes a long time for these missions to come to reality. At that time, there had not been a decadal survey recommending this particular mission, and the technology, you might argue, was perhaps not as mature as it is now. So NASA, in their wisdom, chose to wait until the technology matured, and the community was clamoring for these observations before they decided to fund it.
So I got another one for you. So I know NISAR hasn't launched yet, but with some of the other missions that you worked on and data that you've seen, what are the major, Marcelo on Facebook asked, what are the major differences that you guys have seen from the last 10 years and now?
I'm sorry, I missed the beginning part of that. The differences in what between the last 10 years and now? The Earth?
Just in Earth, and anything that we've seen on Earth or measured on Earth, if you want to pick a specific scientific study.
Maybe something that you'll be looking at with NISAR that you've really been seeing changing in the last decade or so. Certainly ice laws.
Well, I
right?
think, I think the ice sheets is really what I would focus on here, because they are changing quite dramatically, and our understanding of the ice sheets is changing quite dramatically as we make these observations. I'm sorry about the dinging. My wife is texting my children, and I thought I turned off the message app, but I guess I didn't. I apologize.
The joy of live streaming.
Hey, we're glad to hear the family's doing well.
Yeah.
Any more questions, Shannon?
Yeah, I have another one for you. So with the current world situation, Coop on Facebook asks, what data points does this give us that we may not have otherwise been able to get?
Are we talking the current situation, meaning the coronavirus situation, or what?
With people sort of staying inside, is it giving us different data points that we wouldn't normally be able to get in any other situation?
Yes, it's actually very fascinating. NISAR itself is a radar. It doesn't measure the atmosphere, but already we are seeing the impacts on the Earth by having people staying inside, not traveling as much. The air is cleaner. Their congestion is lower. I've seen some radar images actually over the last several months where construction sites, which you can see has sort of in a change map setting, construction sites have stopped working. So you can actually track the impacts of humans and their behaviors over this cycle. And if this continues for a year or so, which it may very well, at some level, we can really understand it's almost like an experiment in a way where you have a stimulus, which happens to be, in this case, people staying at home, and then you can see how the Earth responds to it using all the satellites that are up there. It's really quite astounding. It will be very interesting. We don't really know yet because we're still early in the whole cycle, but about a year from now, you'll see some amazing results come out, I think.
And I have
Maybe
one more
last
from
question.
you. Yeah, one more. So a question from Numquam on YouTube asks, how long will it take to process NISAR data? I know we've talked about this in some conversations with each other about how large the data coming down from NISAR is. So how long is that going to take to process for people to start their research?
It will only take a day or two for the data to go from the satellite to the archive. There is about a 5 or 6 month period when we will be fiddling with the data to make sure it's right. Those data will still be available quickly, but they may get reprocessed after 6 months or so. But once the fire hose of data starts, after about 3 months after launch, that fire hose is ready with lots and lots of data with a latency of just a couple days.
Well, did you? If I missed it, I apologize. But did you tell us that huge number? That it was something ridiculous amount of data that you're going to be pulling down. Like in the first year, you told us, when we first started talking about this. What is the amount of data you're going to be pulling down with this thing?
So it's hard to put it in terms that most people, I think, could actually imagine. But it's basically 1 petabyte of raw data per year. Petabyte, not wow. The CD is what 650 megabytes or something like that. DVD is 5 gigabytes. This is a petabyte, which is several orders of magnitude above those. And that's just the raw data. After we process the data, it cuts to something more like 50 to 100 petabytes. So it's a huge amount of data by the standards. In fact, if you take all of NASA's previous missions, including planetary and space, and add them all up, this is still about a factor of, I think, 10 greater than all of that other data. So it's a very large amount of data.
It's amazing, truly amazing.
But we know how to process it, and we shall.
That is good news. Well, we're getting near the end of our time. But before we wrap up, we have something kind of special to share with you. In advance of Earth Day, when we all try to think more about our shared responsibility to care for our planet, Shannon here asked some friends to answer a question for us so that we could share their responses. And we asked them, what does it mean to care for something? Here's what they had to say.
Hi there, Shannon from NASA Earth. And as we observe the 50th anniversary of Earth Day of this amazing, beautiful planet of ours, we wanted some of our friends to join into the conversation. So we had a question for them. What do you think it means to care for something?
I think what it means to care for something is to protect it and to make it flourish.
To love other people.
For you to care for something, that means you will treat it like it's your own baby, like you will treat it special.
It means giving my unconditional time, effort, emotional commitment.
I think it means to take care of them and to love them in your own unique way.
Like for example, with a plant, if to take care of it, you have to do water and sun and make sure it grows well. It means life to us.
It means when you show like affection or love. If it's a thing, you're responsible with it.
When you take care of something else, you connect with something greater than yourself.
Bye-bye. See you later, alligator.
Oh, that is outstanding. Any thoughts on that from you guys? I mean, Shannon,
it was beautiful.
Yeah, as we celebrate Earth Day, just remember to take care of our pale blue dot.
And what were you thinking there, Paul?
I was just going to say, for me, when I thought about this, I thought respect, caring, and respect are highly related. We need to respect our planet to take care of it. So let's do that.
I wholeheartedly agree. I like how the first young person put it, that to care for something means to protect it, but also to make it flourish. I love that.
Mm-hmm.
Well, thank you, Shannon, for putting that video together. All right, well, that is a great place for us to end this month. I want to thank Paul Rosen for being with us. Paul, good luck to you and your NISAR team with the mission and keeping it on track during these really extraordinary times. Thank you, Shannon Forrey, for helping with the questions from our live audience. And thank you, all of you, for watching and for submitting your questions. And again, if you'd like information and resources from NASA related to Earth Day, you can go to nasa.gov/Earth Day for a whole slew of materials now and over the next several days as we reach the 50th anniversary of Earth Day on April 22nd. Okay, now remember, everybody, deep breath. We're all in this together. We're hurtling through space on our pale blue dot, as Shannon mentioned. And for half a century now, we have had an annual reminder on Earth Day that caring for our home planet and all of us on it is something that we do together. All right, that's all for this month. Note that we do plan to bring you our scheduled show for May, which is on becoming a NASA engineer, and that'll be hosted by my colleague Brian White, and he'll be talking with the wonderful Tracy Drain. So join us for that if you can. Until then, stay safe, take care, bye for now.